Dear student friends, we are studying Lagrange's linear partial differential equation of first order, and in the last lecture we have studied the method to solve Lagrange's linear partial differential equation. So I have written it what we have studied last time, because we are going to use this for solving the problems on Lagrange's linear PDE. See, this is the equation which is known as Lagrange's linear partial differential equation, capital P into small p plus capital Q into small q is equal to R, where these capital P, Q and R are functions of x, y, z. Now, to solve this equation, we have to write its auxiliary equation, and the auxiliary equations are dx upon p. We have studied this method earlier. So the solution of this is the first equation is of this type, but again we have to find out u and v and two functions such that u is equal to c1, v is equal to c2, and these are the solutions of this equation. And therefore, thus once u and v are obtained, pi of u and v is equal to 0 is the solution of the Lagrange's linear partial differential equation. So thus from the original linear PDE, we have to write its auxiliary equation, and then this second equation is to be solved to get u is equal to c1 and v is equal to c2 by grouping method or by the method of multipliers. So the method of multipliers is the property of ratio, and I have written here that property of ratio. Now if these are the ratios, x upon a is equal to y by b is equal to z by c, then we can take multipliers L, M, N. L, M, N are real numbers, or maybe the variables multiples of x, y, z also, or any multiple of a, b, c may be there. Then taking multiplier L, M, N, we have each ratio is equal to, the ratio is x upon a, etc., and this is equal to, that is equal to n into x plus m into y plus n into z is the numerator, and at the denominator also we have to multiply the respective terms at the denominator by the same multiplier L, M, N, and then add it. So therefore each ratio becomes like this. You can verify by taking any proportionality, and then this you can verify. So, and now we are considering the problems on PD. So for example, if we take the ratio like this, see it is 2 by 3, which is same as 6 by 9, which is same as you can take any multiplier as the numbers and multiply these respectively and verify. We can verify this property. Now these are some problems I have listed here. We will solve these problems one by one. Solve the following PDEs. The first is y square z divided by x into p plus zx into q is equal to y square. This is the first problem, Lagrange's linear partial differential equation. And why? Because it is of the type capital P into p plus capital Q into q and is equal to r. So where capital P is this value, capital Q is z into x, and capital R is y square. So we will consider the solution of the first. And then we have to write the auxiliary equation that here we have written. Solution for first. Comparing the given equation, PDE with this Lagrange's equation, it is of this type. We have what is capital P is y square z divided by x, capital Q is z into x, and capital R is y square. So after writing the values of P, capital P, Q, R, we write the auxiliary equation. Lagrange's auxiliary equations are and we know these are dx divided by capital P, dy by capital Q, and dz by capital R, or that is dx upon what is capital P, that is y square z divided by x is equal to dy by z into x and is equal to dz by y square. We can simplify this, and this can be written, this x term is the denominator of denominator, which is actually the numerator, and we shall write x dx divided by y square z is equal to dy divided by z into x is equal to dz divided by y square. Yes, and now this is our Lagrange's auxiliary equations, these are, and we have to solve these equations by taking any two ratio that gives one solution, and another two ratios to get another solution, or use the method of multipliers. Now what we can observe here is we can equate the first and second ratio or fractions, so that this is to be done by observation, and then we have to get the solution, means we have to integrate it. And now see, the first is in terms of x, dA differential of x y square and z. The second is dy divided by z into x. Now if we equate these, or if you take these two first two ratios, then z can be cancelled, and the remaining ratio remains in terms of x, y, z. We can separate the variable and integrate it. So therefore it is useful to take first two fractions. So we may suppose this as 1, taking first two fractions. So what we have is x dx divided by y square z is equal to dy divided by z into x. So we have taken first fraction and second fraction, equated. And then from this we may observe z can be eliminated from both sides, and what remains is so this is the method of this is the property of ratio, and we have to use it. Now after cancelling z or eliminating z from either side, we get that as x dx divided by y square is equal to, the right side is dy upon x. Now to separate the variables, we can cross multiply. This is x into x, that is x square into dx, and this is y square into dy. So easy to get. And now these are in separate variables, we can easily integrate. Integrating we get now what is integration of this? X square into dx, that is x cube by 3. Directly we write, and this is y cube by 3. And a constant of integration we will write in this form, same form, so that we can cancel 1 by 3 throughout. And that is, or therefore we can write x cube minus y cube is equal to c1, and we suppose this as second. So one solution we have obtained as u is equal to c1. U is function of x and y. Now to get the another, what can be done to get the another solution? Now for this purpose we may see now which ratios can be equated. We observe here, if we equate the second and third, but here it is z into z and x, and here it is y square. X is there, x cannot be eliminated from these two ratios, and therefore instead we think about the first ratio, first fraction and the last fraction, equating the first and the third fraction. So what we can observe is this y square and this y square can be cancelled, and the remaining equation will be only in terms of x and z and their differentials. So therefore that will become useful. So our next step will be equate the first and third fraction. Equating the first and third fractions or ratios. We have, see, it is x dx, x into dx divided by y square into z is equal to dz by y square. Y square cancelled from both sides or eliminated from denominator, and that gives x into dx divided by z is equal to dz. And as earlier separate the variable, we can cross multiply, and that gives multiply both sides by z, or that is x dx is equal to z into dz. It is in separate variable, integrating we get. Now what is the integration of this? It is x square by 2 and right side z square by 2 plus a constant. Now the constant we write as c2 divided by 2, and thus that gives x square, we shift this z square on left side, minus z square is equal to c2, and we suppose this as third equation. So this 2 is the solution. We have two solutions we opted. One is u is equal to c1 and another is v is equal to c2 for the Lagrange's auxiliary equations, and the solution of the original equation will be phi of u and v is equal to 0, and therefore from 2 and 3 the general integral of given equation is phi of u is x cube minus y cube is equal to c1, that is phi of x cube minus y cube, comma x square minus z square is equal to 0, or that can also be written as x cube minus y cube is equal to psi of function of x square minus z square. So in either form the solution can be written. So this is the method that we have already derived, and that the same method we have used to solve the first problem. Now we shall consider the solution for the second problem. The method is the same for each Lagrange's linear PDE. To solve Lagrange's linear PDE, solution second. Again comparing this with the equation capital P into P, etc. Comparing the given equation with so what is capital P? We can see it is y square plus z square minus x square, and capital Q is negative 2xy. This minus sign also we have to take, and this is to be considered r on the right side, and that must be negative. R is equal to negative 2zx. These are the values of PQR. Lagrange's auxiliary equations are and we know that r dx divided by capital X, dy divided by capital Q, and dz divided by capital R. that is dx upon, put the values of capital P, Q, R. So it is y square plus z square minus x. And we may suppose this as equations 1 for reference, because we want to solve these equations, auxiliary equations. And we'll get two separate solutions, and then the function phi of these two solutions is the solution of the original equation second, this one. Now which two ratios we should equate, that is to be decided by observation. So take or pick up two ratios such that we can easily separate the variable. If you observe the first and second ratio, here nothing can be cancelled from the denominator, because it is addition subtraction of this and not a product. So this cannot be cancelled. And if you think about the second and third ratio, if you equate these two or we pick up these two ratios, then we can observe minus 2 cancels from both sides, and also x cancels. After cancelling x, what remains? Y and z. And we can separate the variables because there are differentials of y and z. So we take the last two fractions. Taking the last two fractions, we have dy divided by minus of 2x into y is equal to dz, and that implies, so what this implies is dy upon y, negative 2x is cancelled from both sides, is equal to dz divided by z, and this is in separate variable form. We can easily integrate. Integrating, we get, on integration, this implies log y. Integration of dy upon y is log y, and right side integration is log z, and we also consider the constant in terms of log of c1, and thus further this implies log of y minus log z is equal to log of c1, or by using law of logarithm, this is log of y divided by z is equal to log of c1. Eliminate log on both sides, and that gives y upon z is equal to c1. So thus we have obtained one solution from the equations 1, equating the first and the last ratio. Now what we shall consider from 1 again go to 1 to find out the second solution. Go to this equation 1. Now what can be done? So equating first and second is not useful, that we have observed earlier. So we have equated the second and third. Now if we equate the first and the last, whether it is useful. So that is also not useful, because nothing can be cancelled from these two terms. And therefore we should think about the multipliers. And the multipliers we can consider as, say, 2x, 2y and 2z. Then we will observe what we shall get. Next I am writing here. So I will write here. Now taking multipliers. Two x, 2y, 2z. In 1 we have each ratio is equal to, this is the property that earlier we have written. We have each ratio is equal to, and how to take the multiplier? We have to multiply this first ratio by 2x at both numerator and denominator. We have to multiply the second ratio by 2y. We have to multiply the third ratio by 2z. How these are considered? That is by observation. Why we are doing this? Because if you multiply, we have to observe the terms at the denominator. and if multiply this by 2x, what we shall get is 2xy square plus 2x into z square minus 2x square, and then this will be negative 4xy square, and this will be negative xz square, and after adding this we shall get a relation that can be factored. So first we will take this and see what happens. Then what we get is 2x into dx plus 2y into dy plus 2z into dz divided by this is 2x into y square plus z square minus x, and this is plus 2y into minus 2xy, and this is plus 2z into minus 2z into x. So this we have obtained, and now this is equal to 2x into dx. The numerator we keep as it is, we shall simplify the denominator, and you may see what is the simplification for the denominator. We can have, it is 2x y square plus 2x z square minus 2x square, and then this is minus 4xy square. It is here it is plus 2 y square x, and here it is minus 4 y square x. So that means negative y square x remains, and again from this x z square 2xz into z square, and here it is minus 4 into z square x. So that means the terms are like this, 2xy square from first, and here it is minus 4xy square. So that will be minus 2xy square. And next same terms, similar terms, 2xz square minus 4xz square. So this gives negative 2xy square. This gives negative 2xz square, and one term remaining here is negative 2x square. So these are the terms that we have obtained. Now from this what we shall consider is a common term. What is common is negative 2x is common. So this is, I shall write here, each ratio is equal to no change in numerator and if we take negative 2x common, then what remains in bracket is y square plus z square plus x. So that will remain inside the bracket, or but whether it will be useful. So this is minus 2x into bracket y square minus z square plus z square it will be, and this is minus 2x square. So if we take not minus 2x common, so yes, with minus 2x is common, and then it is y square plus z square minus is common plus x. Y square plus z square plus x is common, that we are getting. So whether will it be useful for this? Each ratio we obtain, and we can equate this to which one? If we equate this to this last one, then minus 2x cancels, and but their x remains. So these are the multipliers we are having here, 2x, 2y, 2z. Instead of 2, if we consider only x, y, z, then 2 will not be obtained here. But that makes no difference. And negative 2x is common, y square plus z square minus c, it is plus x. At the numerator it is. So we have to check whether this is the same we have obtained, 2xy square and minus 4xy square. 2 minus 4 is minus 2. 2xz square minus 4xz square, that is minus 2xz square, and this is minus 2x square, that is right. And what is common is minus 2x, then in bracket what remains is y square plus z square plus x, that remains. And we can equate this to which one? So if you equate this to the last ratio dz divided by this, so negative 2x cancels, and what we get is y square plus z square plus, so it must remain x square in bracket. So one correction must be there. This is, see the problem, it is y square plus z square minus x square, and we wrongly written here it is x, so it must be x square. We have to correct it. Minus 2xy is the denominator of this, and plus after transferring this, shifting on this, that is negative. So this is the correction. So it must be x square, and now this is minus 2x cube. So this is the correction you should note. And that makes no difference in earlier part, because we have not equated first, we have equated these two. So there is correction in the first fraction. Instead of x, this is x square, and now it is like this. So take negative 2x common, and in bracket what remains is y square plus z square and plus x square. So this remains. Now we equate this this ratio. Each ratio are equal. Now earlier there are three ratios or three fractions, and these all the three are equal to this. So we equate this to the last fraction of 1. Equate this to the last fraction of 1, because 2x or it can be equated to the second fraction of 1. Anyway, so we equate, because 2x is also there here, and here it is also 2x, and so we can equate this to the second fraction of 1. Equating this to second fraction of 1. We get now see what we shall get is 2x dx plus 2y dy plus 2z into dz divided by. Now shall I write directly, because I shall write as it is 2x into, instead of y square plus z square plus x square, I shall write x square plus y square plus z square, and is equal to second fraction we are going to equate dy divided by negative 2xy. Now this negative 2x cancels from both sides, from the denominator, and what remains is this one. But this implies the numerator is actually d of differential of x square plus y square plus z square, and the denominator remains after cancelling this 2x, x square plus y square plus z square, and is equal to dy divided by y. Both we have written in the form total differential of x square plus y square plus z square, because or otherwise the derivative of the denominator is at the numerator after cancelling 2x. See, the denominator is x square plus y square plus z square, and what is the differential? 2x dx plus 2y dy plus 2z dz, or that is differential of x square plus y square plus z square. So this is written in this form, d form, differential form, total differential, and this is dy upon y. Now it is easily integrable. So integrating this, what we get? same, integrating we get we know integration of dy by y is log y. Similarly, this is in the same form. It is log of denominator, log of x square plus y square plus z square, and is equal to log y plus log c2. And that implies, after shifting this log on this side and using law of logarithm, this implies x square plus y square plus z square divided by y is equal to c2. And this is our second equation, third equation. First we have referred this as Lagrange's linear equation. And what was the second we have obtained, equating the last two ratios after cancelling 2x, that was y upon z. The second equation we have already written here is y upon z is equal to c1. That was second. And thus from 2 and 3 the solution can be written. Therefore, from 2 and 3, the general integral is general integral of given equation or the required general integral is phi of first is y by z and second is x square plus y square plus z square divided by y is equal to 0, or that may also be written as y upon z is equal to, this one is function of second, psi of another function, psi of x square plus y square plus z square. These are arbitrary functions, so only we have to write the solution in this form. So thus this completes the solution of second. Now what remains is the third problem. So we will solve third. Solution for 3. So we have here. Now I shall write directly the values of P, Q, R. Here this is P, capital Q and capital R. We have capital P is mz minus ny, capital Q is nx minus lz, and capital R is ly minus nx. Lagrange's auxiliary equations are and these are, so we know which are dx upon p is equal to dy upon q is equal to dz upon r, or that is dx upon what is p is mz minus ny and q is nx minus lz, and here r is ly minus nx. Now again this is to be observed. Now whether equating any two ratio is useful or helpful. Now equating any two ratio doesn't help us, because there are the terms of again x, y, z is also there, and which cannot be cancelled. So we have to think about the multipliers, and we shall suppose this as 1. Now this is the equation in terms of variable x, y, z, and also the constants. Here L, M, N are to be considered as constants. So if you take the multipliers as in earlier case, here we will take the multipliers x, y, z. Then see what happens. Taking multipliers x, y, z. So we have each ratio is equal to. Now to write each ratio, if you take the multiply first ratio by x, second ratio by y, third ratio by z, and add it. So that is x dx plus y into dy plus z into dz divided by. Now if you multiply this by x, then it can be written as x into mz minus ny plus y into nx minus lz, and plus the next will be z into this, z into ly minus mx. So this we have obtained, and you see that can be simplified further too. The numerator is the same. What is important is the denominator, and what is the expression at the denominator. So this is equal to x dx plus y dy plus z dz divided by. Now x mz, here is also minus mxz, that is negative of each other, minus n into xy plus n into xy, that cancels, and minus l z into y and plus l z into y. So each term gets cancelled and the denominator becomes 0. So what this implies, in the ratio, if the linear multiplier gives one numerator or denominator is 0, then the other must also be 0. Because if we have, say, 4 divided by 3 is equal to, say, 6 divided by 9, and if I take the multiplier as here, say, or 3, and this implies the multiplier as 3, 2 into 3, and here the multiplier as 1, negative 1. So what is the denominator? 3 into 3 and plus 9 into minus 1. So what that gives, if the denominator is 0, the numerator is also 0. That means this implies the numerator is 0. So this implies x dx. We can't say this is indeterminate or not defined. This is a ratio, and if in the ratio combination gives one denominator is 0, then the numerator must at the same time will be 0. This is an example. Y dy plus z dz is equal to 0. This can be easily integrable because it is separate variable form. On integration or integrating, we get x square by 2, actually y square by 2 plus z square by 2 is equal to c1 by 2, and we cancel throughout 2, and that is, this implies x square plus y square plus z square is equal to c1, and this is our first solution. We refer this as second. So thus we have used the method of multiplier. Now again we can think about another multipliers. Instead of x, y, z, we can consider here the multipliers L, M, N, and that will again give the same type of results that can be verified now taking multipliers. So this is to be done by observation only. How we have to observe the terms, and we can use the trial error method. Either equate any two fractions which cancels, etc. Think about that. There are only two methods: group the ratio and make a separate variable so as to get the integration, or think about the multipliers. Multipliers may be variables as we have seen here. Now the multipliers can be taken as taking multipliers LMN in 1. Each ratio is equal to, and if you take the multiplier, means we have to multiply them both numerator and denominator by L. So that is L into dx, second M into dy, and third multiplier is N into dz divided by, and the denominator is L into mz minus ny plus M into nx minus lz, and plus N into ly minus mx, or this is equal. Now you can observe the denominator. See what are the terms at the denominator. It is LMZ, and this is minus LMZ. This is minus LNY, and here it is plus NLY. That cancels, and minus MLZ, and this is see plus LMZ cancels. So that means each term gets cancelled, and this is 0. So as earlier, if the denominator is 0, the numerator must be 0. So this implies L dx plus m dy plus n dz is equal to 0. Integrating, this implies L, M, N are constants and integration of dx is x. L into x plus m into y plus n into z is equal to constant. And this is our second solution. Therefore, the general integral is phi function of this. First is x square plus y square plus z square, and second is lx plus my plus nz is equal to 0. Or that can be written as 1 is function of second, and that function is denoted by psi. Here we denote the function by psi, here phi we denote by psi, or vice versa, or any other f, g, etc. These are arbitrary functions. But what are important are these solutions. These must be the same. Function may be denoted by any letter, and this is psi of. So this is the solution. And only the last problem is remaining. We will solve that also. So it is our fourth solution for fourth example. And again, comparing this with the Lagrange's equations, we get solution for 4. We have what is P is x square minus yz. Q is y square minus zx, and R is z square minus xy. Therefore, Lagrange's auxiliary equations are, and these are as we know earlier, or that is and here also see equating or taking any two ratio doesn't work or is not useful, and therefore now what can be done is each ratio actually can be taken as a first and second ratio, and we subtract or add it. So that is same thing as multiplier. So what we are doing actually is take the multiplier as 1 1 and minus 1 1 1 and 0. So what that gives, dx or 1 minus 1 dx minus dy only, and this is 0 means it is not considered. So dx minus dy, that will give. And second thing, we can consider the difference of these two. Then the multiplier will be 0 1 minus 1, and then that will give dy minus dz. And finally we take the difference of these two, that is first 1 0 minus 1, that will give dx minus dz. So therefore each ratio is equal to, now suppose this as 1, each ratio is equal to dx minus dy. Subtract the numerator of the first two fractions and denominator of the first two fractions. So this will give x square minus y square, and minus this is plus. So we may consider z is common, and I shall write this as x square minus y square, and then this is positive plus z x minus y. You can verify this subtraction of these two. I have written this positive z first and then minus y. Similarly, this is equal to dy minus dz. Here it is y square minus z square, and then we'll take what is plus x common, and in bracket remains y minus z, and is equal to dx minus dz. Dx minus dz, x square minus z square, and plus. So here I shall take y common, plus y is common, then that is in bracket it remains x and minus z. So what that further implies is, at the denominator we can factorize. At denominator, what are the factors you may see, and the factors are here x minus y, x plus y, and then x minus y is common, so that can be done. So this implies dx minus dy divided by x minus y is a common factor, and in bracket what remains, here x plus y remains and here z remains. So this is the arithmetic part you can verify easily. Factoring this, x minus y is common factor, remaining is written in bracket. Similarly, this is dy minus dz. Factorize this y square minus z square, y minus z into y plus z. Y minus z is common, and if we take y minus z common, in another bracket it remains x plus y plus z. And this is equal to dx minus dz. Again factorize this, x minus z is common. Now we may observe here. So we are seeing, instead of considering this as first, we may consider this one as first, because we are going to refer this. And now we can equate the first two ratio, any two, so that this term gets cancelled. So this implies taking first two fractions. So, and I shall write, we get dx minus dy divided by, after cancelling this I shall write x minus y is equal to dy minus dz divided by y minus z. So this we shall get, equating these two, cancelling the factor. And now this is integrable. Actually the numerator is differential of x minus y, that is d of x minus y dx minus dy divided by x minus y is equal to d of y minus z divided by y minus z, and integrating we get. Now what is the integration of this? Log of x minus y is equal to log of, and the integration on right is y minus z plus log of c1. Or therefore this is, now see, as in earlier shift this on left side, and that implies x minus y divided by, after cancelling log on both sides, divided by y minus z is equal to c1, and this can be taken as second. Now what can be done for the second solution? Now you may observe easily from one. Now equate second and third, or equate first and third, any. This factor cancels and we get another solution. So equate taking last two fractions. Fractions from 1. We get, now what we get is dy minus dz divided by y minus z is equal to dx minus dz divided by x minus z. Integrating, this gives, I shall write direct solution, log of y minus z, and this is log of x minus z. So that gives, after cancelling the terms etc., this is z is equal to c2, and this is third. And thus from 2 and 3 the general integral is the required general integral of original solution is pi of x minus y divided by y minus z, comma y minus z divided by x minus z is equal to 0, or that can be expressed as psi of second function. Thus, one thing is to be, this gives the solution, and one thing is to be noted that we have equated the last two fractions. Now instead of equating last two fractions, we can equate first and last. In that case, what will be the solution? The solution will be in that case x minus y divided by x minus z, instead of this y minus z divided by x minus z. But that is equivalent, and that is also correct. So it is not necessary that we should equate first two and the last two. We can equate the first and the last also. So there will be change in the form of the solution. Instead of y minus z, there will be x minus z, x minus y, and then at the denominator will be the same, x minus z. So this may happen in the solution. So both solutions will be correct. So these are the methods that we have used to solve Lagrange's linear partial differential equation. Two methods, grouping and multipliers, and that is to be decided by observation only, or by trial and error, or by practice. So the remaining part we will continue next time. Thank you.